8 here, less than 8. Yep, I think we're good. We're going to talk a little bit about molecular compounds. We wrote these notes yesterday. We're going to put our phones away right now. And we talked about, real quick here, just a quick review. Covalent bonds is what we're going to talk about. Sharing of electrons by nonmetals, of course. Maybe 2 nonmetals, maybe more than 2. We'll see. Compounds in which atoms are covalently bonded together are called molecular compounds. And of course, we're going to use Lewis structures to help us with that. Okay. We had all these notes here yesterday. Rules for drawing simple polyatomic or molecules and polyatomic ions. Hopefully we'll get to the polyatomic ions, but I can't promise that today. But we're going to add up some valence electrons. And valence electrons, of course, we're going to get from the Lewis diagram, yes? So electron dot diagram or Lewis diagram, that's where we're going to add up electrons from. Now, again, we'll have to add or subtract some electrons if there's a charge associated with it. So, for example, if I was just going to draw CH4, which was our first one, did we draw any yesterday or no? No? Perfect. So if we're going to draw CH4, we're just going to add up all the electrons that are available there for us. And I'm going to show you a couple of different ways to do this. But if we're going to draw SO4 2-, which is sulfate, I guess I should have picked sulfite. But if we're going to draw SO4 2-, what does 2- imply? We've gained 2 electrons, yes? So we need to add that in, and that's kind of what it's saying here. We might have to put some extra electrons in there, or maybe get rid of a couple if we're going to draw a positive ion, like NH4 1+. That means we've lost an electron, all right? So that's what that's implying. We'll talk about that. We're going to choose the atom with the most unpaired electrons, and we're going to talk about something called bonding capacity today. So how many bonds can this atom form? If it forms like the one that has the best bonding capacity or the most unpaired electrons, we want that to go in the middle because that's where we're going to connect all the stuff to the middle atom kind of thing. All right. We talked about we're going to draw a skeleton structure, so we're going to put atoms around that central atom. Basically, we're going to, if that's the central atom and we want to put it in the middle, we're going to draw some atoms around it basically, and then we're going to basically connect the outside atoms to the central atom, and I'll show you that in a second here. And then we get all this stuff, and this is where it gets a little confusing here. I think we have this copied, yes, correct? Yeah, unless you weren't here yesterday, but then of course you went to Google Classroom and copied down all the notes, or printed them off at least, obviously. So it says place lone pairs on the outside atoms first, so we'll talk about that. And then if the outside atoms are good, then we're going to start shifting some around, and if we have extras left over, we're going to put them on the middle atom, central atom, and if we don't have enough, we're going to move some stuff around, and that's basically very, very simplistic form of this, okay, from yesterday. So first example, you ready? Yes? All right, here we go. So I'm going to show you 2 different ways to do these, and I'm going to go through kind of the rules as well and whatnot. But the first one we're going to look at is carbon tetrahydride. And if you remember back to when we drew ionic compounds, what's the first thing we need to do? What's step 1 always? Come on. Huh? Write out the formula, carbon tetrahydride. Write out the formula. What's next? What do we do next? What do we do with ionic? We started with what? Somebody, anyone, come on. What's the next thing we did with ionic compounds even? We started with? Nope. Oh boy. Chirp, chirp, crickets. What do we do with ionic compounds? What's the first, what do we start with? We start with, yes, of neutral atoms. Neutral atoms, yes. So we're going to start with some neutral atoms here. There's carbon, it's got 4 valence electrons, yes. And each hydrogen, of course, has 1. And we need 4 of them, right? So we start with some neutral atoms. We draw basically some Lewis diagrams for those. Carbon has 4, count across, 1, 2, 3, 4. Hydrogen's got 1, yes? Okay. Now, I'm going to kind of mix what I'm going to do here with some of the rules. And you're going to kind of see that maybe we don't need the rules for everything. Sometimes they just fit together pretty nicely. Sometimes the rules are very helpful as well, so it just kind of depends. But I'll show you both options here. Let's talk about something called bonding. Like I said before, we're going to talk about bonding capacity. Okay, and I'm going to introduce another term to you coming up here as well, but we'll wait for that. Bonding capacity. What's the bonding capacity of carbon? How many bonds do you think carbon can form? Robbie? 4. Okay, so it's got 4 unpaired electrons, 1, 2, 3, and 4, yes. So it has a bonding capacity of 4. If there's going to be gaining and losing or sharing in this case, it's going to happen with those 4 electrons, yes? So this has a bonding capacity of 4. What's hydrogen's bonding capacity? It's not your question. 1, okay? So it's got 1 unpaired electron. It can form 1 bond, basically, yes? So all those are 1s, yes? Okay? So it says in the notes, and like I said, I'm going to kind of use a little bit of that stuff because it applies no matter what. Which one would we want to use as the central atom? Carbon or hydrogen? Carbon, because it has the best bonding capacity, the most bonding capacity, or it has the most unpaired electrons. So we're going to put carbon in the middle, the central atom. That's going to be my central atom. That's everything else has to go around that. Okay, and then I got these 4 hydrogens, and lo and behold, look, I can put a hydrogen here, I can put one here, I can put one here, and I can put one here. Yes? Okay. And you've actually just drawn carbon tetrahydride, otherwise known as methane. Now, you might see this. Okay, so this is a drawing that you might see on a quiz or a test someday or whatever. Okay, that's an option. You might see this. Let me just show you another option here. So they might actually show you that the dots come from the carbon, and they might use, like, for example, I'm just going to say like an X for the hydrogens, which basically means it's the electron that comes from the hydrogen. That's all. Okay, it's no big deal. Whatever, doesn't matter. Okay, so you might see that. You might see this, and this is probably the most common thing, which of course looks a little something like this here. Okay, and we're going to draw lines to usually that's the one we're going to see. We're going to draw lines to represent a pair of electrons, which of course is known as, I think you already know this, I believe, but this is a covalent bond. Okay, 2 electrons, yes, that are shared. All right, covalent bond. Yep. Huh? Okay. So those are the 2 electrons that are being shared there, and I'll kind of go through that real quick here before we move on. But what was I going to say? Something here. What? That's probably the most common one. Oh, I know. Notice how the difference, right? Ionic, we use arrows, right? And then we show the electrons and charges, like we did 2 days ago, I guess, yes? We went over that homework yesterday at the beginning. This is a 1 line, yes? And that's the sharing of electrons. So keep that in mind, all right? Basically how this works is this. Look, does hydrogen have 2 electrons? Remember, hydrogen wants to have 2 electrons. You don't have to draw this part, but if you want to, you can. But hydrogen has 2 electrons around it, right? That's how it becomes more stable, right? Hydrogen wants to have 2 electrons around it. The hydrogen's there, and if it could gain another electron or could have another electron, it'd be more like helium, yes? 2 in the first energy level. So here's hydrogen, it has 2 electrons around it. Here's hydrogen, it's got 2. Hydrogen's got 2. Hydrogen's got 2, right? So we all have 2 electrons around the hydrogens, and then carbon, if it wants to become more stable, it needs to have 8. Does it have 8? Well, 2, 4, 6, 8, yes? So carbon has 8 around it. And again, if you draw it with like that kind of idea in mind, they're going to be right, right? Carbon, like I said, every element wants to have the octet to become more stable. Hydrogen, of course, wants to have 2. There's actually one exception to this rule, but that's okay, all right? Or maybe a couple, but we're only going to look at one. Okay, so that's carbon tetrahydride. Now, let's take a look here for a second. If I was going to follow the rules identical, like exactly word for word, like step by step, this is what it looks like. So if I was going to follow those rules, okay, like I said, I don't know if we really need to in this case because they seem to match up pretty nicely, don't they? You know, carbon has 4 free electrons. Each hydrogen kind of goes like boom, 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 and we're done, yes? So I don't know if we need to spend a lot of time going through, you know, 8 rules and asking questions and all this stuff when they just match up, right? Even with the next one we do, you're going to find that they match up pretty nicely. So that's kind of up to you. I'll let you decide. But here's an example of CH4 with adding up electrons, like in step 1, add up the electrons. Now, the only difference here is we have to add up all the valence electrons, all right? We're not talking about bonding capacity. We're actually adding up electrons. So carbon has 4, and each hydrogen has 1, yes? So I would still copy this down. We're still going to do both. And the only reason I'm going to say this is because we're going to do this for polyatomic ions. So like SO42 minus, we're going to do this, okay? We cannot just put them together nicely. That's not going to work out for us. That's a total of 8 electrons. So you're going to add them up. So basically what they're saying is, hey, if I want to draw CH4, you have 8 valence electrons that you need to kind of spread throughout this compound nicely, okay? We would start, the second one says, pick the one with the most unpaired electrons or the best bonding capacity and put it in the center. That was step 2. 3, draw a skeleton structure around this one. So I'm going to put my hydrogen, 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 okay? Remember, just a kind of reminder here, now don't maybe do this part, but there's 4 positions around each atom, right? They kind of do this, right? Look, 1, 2, 3, 4, and then if I needed more, right, 5, 6, 7, 8 kind of thing, yes? Kind of like that. So that's where those 4 positions come from. So I'm going to kind of draw this thing here. Now, what was that? That was the third step, I think. Is that right? The fourth one, no, I don't know. I'm confused. The next step after that, after you draw the skeleton structure, it says you need to connect the outside atoms to the middle one because you need to make this a molecule. You need to connect them together somehow. If you don't connect them, we don't have a compound. We just have a bunch of carbons and hydrogens that are floating around. So we need to connect these outside atoms. So we put 2 dots there to represent a covalent bond, basically, because they have to share. And I'd put probably 2 here, and 2 here, and 2 here, okay? And that means, oh, sorry, I shouldn't have done this. 1, 2, now I messed it up. 1, 2, 3, 4, 5, 6, 7, 8. 8, yes, I've used up 8, okay? Now, what you have to remember is, now in this case we're done, but maybe we don't know that. You basically have to ask yourself, are the outside atoms, do they have their octet? Does hydrogen have electrons, the number of electrons it needs to become more stable, basically? And the answer is yes. Hydrogen wants to have 2, yes? So it does. Perfect. And so does this one, and so does this. Well, I shouldn't do that. And so does that one, and that one, and that one. Yes, they all have 2. So we're good. Then you have to ask yourself, is the middle atom happy? Does it have its 8? And the answer is yes, it does, right? So this is a good diagram. We've used all the electrons possible. We're done. Okay, and then we get this, you know, you might see this, or you might see this, okay, where that line represents 2 of those electrons that are paired up, yeah, okay. Now, it depends on the compound. They can get a little more complex, of course, and you'll kind of see what I'm talking about, how we're going to move stuff around and so on and so on. Our next example here happens to be some water, so let's copy that one down. Water, okay. Like Tara said, the first thing we always want to do is write out the formula, right? It doesn't matter if it's ionic or molecular. Very first step is we're going to start with H2O in this case. We're going to start with some neutral atoms. Yes, there we go. Now you're catching on. So there's a hydrogen. There's a hydrogen. Oxygen has 6 valence electrons, yes? Okay, and again, you have to know Lewis diagrams, and you have to do them quickly because this is going to be step 1 of 7 kind of thing, eventually down the road here. So We're going to start with some neutral atoms. Now, eventually, you might be like, after a while, you're going to be like, I don't need to do all this stuff, and that's fine. You just can't screw up the diagram, that's all, okay? You just cannot, because if you do, then everything's going to be wrong. Which one would you put as the central atom, H's or O? Huh? Sorry, I didn't hear. O, right? Yeah, how many, what's the, actually, let me ask you this. What is the bonding capacity of O? Nope. Just kidding, 2, right? 2 unpaired electrons, right? So it's a bonding capacity of 2. And if we want to write, maybe I'll write that down. That's 1, 1, and this is 2 because of those 1, 2. It's got room for two dots there, basically, or 2 electrons, yes? So it's actually only a bonding capacity of 2. If I was going to draw this, this is probably what I would do, okay? I'd just say, well, okay, I'm going to start with O because it's got the best bonding capacity, and there's my O, okay? And then I'd say, okay, how am I going to connect these H's, or is this going to match up nicely? The answer is yes. If I put an H here, boom. If I put an H here, boom, right? Looks like they match up pretty nicely. And if I wanted to, I could actually just go ahead and put some lines here and lines here. Now, if you're going to do this, okay, please, please, if you're going to be lazy, but not too lazy. You know, if you're going to put a line there, make sure that you don't like do like this or something like that, where there's still dots there, because then I don't know if what you're doing, okay? Like I'm saying, like make sure you cover the 2 dots at least, because otherwise it looks like there's dots everywhere, and I don't know if you have extra dots, and I mark it wrong, because I enjoy marking things wrong, okay? No, not true actually, but make sure you make it neat, okay? If you got to redraw it, then redraw it. It's not going to take you that long, okay? That's water, right? Look, does hydrogen have 2? Yep. Does hydrogen have 2? Yep. Does oxygen have 8? Yep. Okay. Good. Okay. Again, I don't know if we need to go through a bunch of rules for that. That's pretty straightforward, and they match up pretty nicely. And a lot of them do, because we're doing simple molecules for the most part. Okay, they're going to match up pretty nicely in a lot of cases. That's why, for example, if we're doing like water, H2O, that's why it matches, you know, common compounds match up really nicely. That's the point. You know, it's weird ones that we wouldn't probably talk about that don't match up nicely, and then we got to do stuff with them. If you want to do the rules, now this is how it changes a little bit, perhaps, okay? I'd say, okay, well, we got a hydrogen, and oxygen. There's 1, 1, and this is now 6 for a total of 8, yes? So this is where we add up the electrons. We add or subtract charges. We don't have any charges to worry about. Perfect. We would start with the central atom, which is O. Now, here comes the issue, and this is why, you remember when we first started drawing Lewis diagrams, I told you, hey, if you're going to draw oxygen, do it like this. 1, 2, 3, 4, 5, 6. Remember that? I said, do that, and then just leave it like that's good. That's fine, right? That's because that's good. That's awesome. I'm going to show you what happens if you try to make things look nice and pretty here, which is going to happen on this. Now, I'd put O in the middle, and if I was going to draw a skeleton structure and I only got 2 atoms, I would try and probably, why would I think that one goes here and one goes here, right? If this is my central atom, wouldn't it make sense to put it there? Yes? I mean, that's what the central atom means. It's in the middle, right? Central. So I'm going to put an H there, okay? And then I'm going to say, okay, I have 8 electrons to use. The document says, or the list of stuff says, I need to connect the outside to the inside. So I'm going to connect this to O and that to O, okay? Then it says you have to make sure that the outside atoms are happy first. It's not about the middle guy. It's not about you, okay? You got to make everybody else happy first. So, is hydrogen happy? Is this hydrogen happy? Okay. So now that those 2 guys are okay, it says in the notes you can now go to the central atom if you have any electrons left over, and you can start putting electrons on the central atom. So I've used 4 electrons so far, and here's 5, 6, okay? And I have to use 8, that's what it says right here, 5, 6, and so I'd probably put the other 7, 8 there, yes? Good? Okay, that's kind of the idea of the rules there in that case. Now, is this wrong? If you drew it like this, I would still give you marks for this. That's fine. However, okay, if you had to pick a shape that this looks like, you'd probably say it's kind of what? Linear-ish, yes? Right? It's all kind of lined up. But the problem is water is not linear. Water is actually, looks like that. It's what we call bent, okay? So that's, in this case, why I kind of like that option better, because it kind of forces you into this bent molecule. Water looks like this, okay? Now, you can still get all the right answers from this, but you have to understand what you're doing. And we're not going to talk about that right now because that's too far. That's going to happen in a few days here. But you can still get all the right answers if you draw it like this, and I'll give you a mark for this. But then the second part is super important, that you understand, hey, this is actually this molecule here, and that maybe I didn't draw it. I'm not saying it's wrong, but probably doesn't quite look like this, okay? So we just have to be aware of that. That's super important, all right? Next, I think we're going to do some, this one here. Oops. Let me see. Yeah, that's right. We're going to do a little carbon dioxide. Carbon dioxide, yeah. Now, this is kind of where you're going to see start to see some differences here, but carbon dioxide will look a little something like this here. Carbon dioxide is what we're going to start with. And again, probably want to start with some neutral atoms, C's and O's. Like so, okay. We can talk about bonding capacity for each one. This is a bonding capacity of 4, yes, carbon. By the way, carbon's really good, and so there's one more atom that's really good that's always going to be in the middle. If you have carbons in your compound, they need to go in the middle, yes? Because nothing else has 4 valence electrons except for silicone, yes? Would be another option. But carbon is like that's why it's so good. You know, we talked about it, I think we talked a little bit about it in ionic compounds. Is carbon going to form a -4 or +4? And the answer is neither, because it's really good at being in the middle of these molecular compounds, right? There's a whole study of chemistry based on it. It's called organic chemistry. Carbon is in the middle, okay? So bonding capacity 4, each oxygen has a bonding capacity of 2, okay? Now remember, bonding capacity is one thing, but if we're going to add up valence electrons, that's different, yes? So don't get those two confused at all here, okay? Now, I put carbon in the middle, and again, if that's going to be my central atom, I'd probably want to put an O on one side and an O on the other side, okay? Like so. Well, that's kind of a little bit messy here. Let me just try to see if I can fix that. Okay. Now, I didn't count up electrons. I'll do that in a second. I didn't follow the rules, right? But I'm just going to kind of start here. Now, remember, regardless of what you want to do here, or what rules or whatever, if you want to follow exactly, the important part here is that, look, you got to connect the outside. You got to connect all the atoms to get, like, at least the outside atoms to the center atom, right? So right there and right there is going to be a bond, yes? Okay, that's the first thing I need to do, because I need to at least make a molecule out of these. I need to make a compound. I need to connect the outside to the inside. The next thing I'd say is, well, does each atom have 8? And the answer is going to be no, and I already know that, because whenever you see electrons by themselves, that means look, everything else is paired up. So if everything's paired up, and then you see electrons by themselves, that's an odd number, yes? Like I can tell you already, there's only going to be like 7 or 5 or something like that, because they're not paired up. So right here, if you're just going to, I'm just going to do this. 1, 2, 3, 4, 5, 6, 7 right here, right? So right around here, that's only 7. That's not good, right? So what we have to do in that case is we have to, of course, maybe pair up a few more. And luckily for us, look, there's 2 electrons right here, 1, 2. So we can pair those 2 electrons up. So we're going to compare combine these two here together, only we're going to obviously probably want to erase that and put that there. And that's called a double covalent bond. All right? And again, if you need to show that, that's fine, you know. And maybe what I'll do is I'm just going to leave these, and I'm just going to show you, well, okay, that's fine. Now, this oxygen, in fact, does have 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes? So that oxygen's good. Carbon still is not, and neither is oxygen, but look, there's unpaired electrons still. So chances are, we probably want to, in this case, take this dot right here and this dot right here. Now you may say, well, it's on top and that one's on the bottom, but remember, we're trying to draw, first of all, we're drawing two-dimensional, okay? And that molecules are not two-dimensional. And secondly, we're trying to draw these molecules with these dots here just to show that they're paired up. But remember, these electrons are going around and around. So they're not even, like I put that dot there and I put that one there, but that's not where they are. They're going around like at 1,000,000 miles an hour. They're going around and around, so who knows where they are? All right? So I'm going to take these two dots here, and I'm going to say, okay, let's put another bond in here. And then I'm going to have that there, okay? So I'm going to connect those two red dots, basically, and put it in that, between the two, between the C and the O, okay? Questions? Questions? Does each one have 8? Yeah. 2, 4, 6, 8. 2, 4, 6, 8. Yes. 2, 4, 6, 8. Right? And that's kind of how they overlap and they help each other out. Yes. Questions? Yeah. Like why is this one like straight across from each other? That's a good question. Well, because because of the 4 spots around it, it's a little different because now what we're doing is carbon has a double bond, which as soon as you put that double bond there, it forces it into a line basically, into that O. And then the other double bond forces it into the O. There's actually with this one, and I know you might disagree, but there's only we don't know this yet because we're getting to that when we get to the shapes, but this is kind of your central atom here, and there's only one thing here and one thing here, okay? So basically it's here, 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 and it's lined up. So I would actually, the shape of this one is actually called linear. Yeah. The difference is when we talk about water, okay, these have to have a position here and a position here, and this has a position and this has a position. So what we get is 4 things around the central atom instead of just 2. So we have 2 atoms still, but we have those lone pairs take up a space, basically. So it forces it into a different, instead of like, you have to have a space, you have to account for those, what we call lone pairs, which I don't think I've mentioned yet, yes? Lone pairs are a pair of electrons that are not involved in the bond making, yes? Okay, so these would be called lone pairs right here, and this is a lone pair right there as well. Okay, they have a space to go to, but because of that, they take up 2 positions, and then the hydrogens take up 2 different ones as well. That's why it doesn't go straight across. But I'm hoping some way, shape, or form, we're going to give you the model kit, and you're going to be able to put these together and see that it actually forces it into certain structures, which we'll talk about eventually. Okay, just not yet. All right. If you want to add up electrons for this one, carbon dioxide, by the way, I can do that as well. Let's do, I'll just do this real quick. It's up to you. This is 4. This is 6 and 6, yes? Remember, you're adding up all the valence electrons. So this is a total of 16 electrons. Yes, 16 altogether. I would still, that's step 1. Step 2, pick your central atom. Step 3, draw a skeleton structure. So I'd still do that. Step 4, connect the outside atoms to the middle one. Like so, yes? Okay, now this is what I'm talking about. You have to make sure the outside atoms get filled up first. They have to be happy before I can do anything else here, okay? So there's 1, 2, 3, 4. I have 16 electrons to use. So here's what I do next. That's 4, 5, 6, 7, 8, 9, 10. Okay. 11, 12, 13, 14, 15, 16. Okay. Yes. That's what the rule says. Basically, the outside atom's got to get happy first. Once you've used up, now, do I have any electrons left over? I've used all 16, yes? So now it says, okay, you've used all 16. The outside guys are happy. Okay, good. Now, what about the middle guy? Is he happy? Does carbon have 8 electrons around it? No. So now what it says in the notes is, if you follow along in the notes there, it'll say, look, if the central atom, if you've used all the electrons, the outside guys are good, but the middle guy's not, you need to move a pair of electrons in to basically make that happen. You might say, okay, well, I'm going to take this, I don't know why, but I chose this pair right here, and I'm going to take this pair, and I'm going to do this. I'm going to move it into there, okay? And you might say, well, what's the big deal there? And the answer is, well, what I'm going to do is I'm going to share those electrons in addition. So those electrons right now only belong to oxygen. They don't belong to the carbon. But when I put them in between the two atoms, now they're being shared between oxygen and carbon, yes? And you might say, well, how do you know it's those two? And the answer is, I have no clue. I don't know. Maybe it was these bottom two, maybe it's those two, and maybe they take turns. Okay, more than likely they take turns sharing. Okay, so I'm going to move that pair in, so it's going to look a little something like this. Okay, does oxygen still have 8? That's important, right? Sure. 1, 2, 3, 4, 5, 6, 7, 8. Right there. Yes, that's 8. Okay, and but by me doing that, and I'm going to do the exact same thing over here. Watch, just because if I just do this. Is carbon good? It's better. It's got 6 now, yes? But it needs 8. So I'm going to take, I don't know, I'm going to take this pair here and shove it into there. Okay? So I'm going to take that pair and shove it into there, and then watch. Okay? Does carbon have 8 now? Yeah. Does oxygen still have 8? Does oxygen still have 8? Yeah. And then, of course, this is how you get your double bond, yes? And your double bond, okay? And there's one more thing I'm going to mention. I'm not too concerned about it today, but just because I know some of you are going to be like, I'm going to do this perfectly today, and then I'm going to do it perfectly later on. That's fine. But we're going to talk about a little concept called VSEPR, which VSEPR, valence shell electron pair repulsion theory. Basically what it says is valence shell electrons pair up and repel each other. So C, double bond O, double bond O. These actually are kind of slightly repelling each other right there. So that pair is actually kind of repelling in the other pair, right? We just have to draw them like that so that we can show that there's a double covalent bond there. That's true. The other electrons will pair up and try to repel each other. So they'll try to take positions a little farther apart. So usually what we do, when you see an accurate diagram of carbon dioxide, you'd see electron pairs over there like that. In other words, they want to get, this pair wants to get away from this pair, and this pair is away from there, and that pair is away from there, if that makes sense. Okay? And that's kind of what we're going to eventually get to down the road here. Same thing here. I'd probably put them like that. Okay? I'll prove it to you on the other diagrams we drew too real quick. Okay? If you look back at this one here, H2O, okay? Here's, I kind of messed up that diagram. So that pair, this pair is away from this pair, and that pair is away from that pair. They're basically as far apart as they're going to get, yes? Okay, those pairs of electrons. Whether it's what we call lone pairs, and it looks like I got a lot of electrons here. Those lone pairs are away from these bonding pairs, basically. Okay, if we're talking about CH4, look, CH4, they're all as far apart as possible from one another, yes? Those bonding pairs, they've taken positions as far apart as possible. So that's what forces them into these shapes that we're going to talk about eventually down the road. Good? Questions, anyone? Moving on. What's next? Okay, I know what's next. Yep. N2. So why does nitrogen come in twos? When you're walking down the street, hey, and you're like, I have no bright or clever friends. People stupid. When you see nitrogen, right, it comes in twos because, again, N's bonding capacity is what now? N. Bonding capacity of 3, yes? And N has 3, yes? And look, I mean, do I really need to go through rules with this one? 3 unpaired electrons, and they don't have 8 each. We got to connect them together somehow, so let's connect them together, right? At least that. And geez, they're still unpaired electrons, so we probably should do something about that. We probably should connect them together. So we're going to connect them together, right? And then look, there's one here, there's one here. Let's connect those together, and you get a really big happy face, yeah? No. You're going to draw it nice and neat, though, yes? So this actually would form a what? Triple bond. And with some lone pairs, right? I probably wouldn't put the lone pairs there because is the lone pair, those lone pairs, are they far enough away from those triple bonds? Not really, right? And you might say, well, these triple, like, shouldn't these kind of spread themselves out? They kind of do in a way. It's kind of hard to explain until we get to the model kit. They kind of do, but we have to kind of represent that. And the only way to represent that accurately is to show that. But probably your best diagram would be something like that, you know, where we put the lone pairs on the ends to get them away from everything else kind of thing, okay? So that's probably a most accurate diagram or drawing of N2. You have to also remember that, like I said before, we're drawing two-dimensional objects. We're drawing them two-dimensionally, and they're actually three-dimensional, right? So sometimes this doesn't make a lot of sense for us, all right? The next one I think we have is this one. Now, this one, I don't know what, well, I do know what this is called, and you will know too when you get to grade 12. But for now, I can't give you like we don't know how to name this, yes? Because we only name 2 atoms, yes? Like carbon tetrahydride or sulfur dioxide or something like that. This has 3 different atoms, and I don't know how to name that unless we're doing organic chemistry right now, okay? Again, you know, I don't know what you're thinking, but I'm thinking there's carbon. It's got 4 hydrogen. I know what that looks like. I kind of know what the CLs look like. I think it's going to match up pretty well. So I'm going to put my hydrogen here. CL looks like this. CL looks like this. And CL looks like this. And again, they kind of match up nicely. And my point to this, doing this one is, you know, same thing. If you think they're going to match up nicely and you can handle that, that's fine. We'll also add up electrons if you want to do it that way. No biggie. That's all good. But that works out pretty well, you know. And a lot of them do work out pretty well. Again, you know, if you want to leave it like that, that's fine. If you want to connect it together, make sure you do it neatly, so we don't see any extra dots or anything like that. Don't make the lines super, super thick or anything like that. Some of you are asking why to put the H on top. Can I put it on the bottom? Can I put it on the side? This is my chance to rebel, you're thinking. Hey, go ahead. Make my day. No, you can put the H wherever you want. Put it on the bottom if you want to be different. Express yourselves. Okay? This is your chance. Put it on the side. I don't care. These molecules turn, right? The atoms turn. The molecules turn. They flip over, et cetera, et cetera. So that would be CHCl3, right? If you want to add up electrons, real quick here, remember, this is 4, this is 1, and each of these are 7, yes? Chlorine has 7 valence electrons. So 7, 7, and 7. And that is a total of 26. And that's probably a little bit more common of what we're going to see for, you know, more complex ones. We're going to get up to 32, et cetera, and a lot more electrons, yes? So again, you still have to understand that, hey, I'm going to put the C in the middle. I have 4 atoms, so I probably put it 4 places around there, try to split them up. You're going to connect the outside to the inside. 1, 2, 3, 4, 5, 6, 7, 8. That's step 1. You have to do that. And you've got to start there because you've got to make those outside atoms connected to the middle one. Otherwise, you don't have a compound, right? That's 8. Should I put any more around hydrogen? No, it's good, right? It's got its 2. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Look at me counting, eh? And you're done. Chlorine's got 8, carbon's got 8 in the middle, hydrogen's got 2, we're good, right? And so that would be kind of what you're doing there. Okay, you don't have to move anything around in that case, they're all good. Good? Questions? All right, last example here, and then I'm going to be quiet here. Two more, sorry, real quick. C2H2, I have to show you this one because I had some questions on this today, which kind of confused me because I know you're getting tired. I get that, especially certain students, okay? Not naming names or pointing fingers, right? I get it, but I'm going to show you this example because there's one exactly like it in the homework today, and then students were like, "How do I do this one?" I was like, "Well, exactly like you do this one. Why would you do it any different?" Carbon, it looks like this, yes, carbon, and we got 2 hydrogens. Okay, now, which one goes in the middle? It's not your question. Yes, kinda. Which one goes in the middle? Which one's the central atom? Just say carbon, because you're never going to be wrong, right? Which carbon you're going to say? Both. Yeah. Carbon's really good. Really good. In fact, this is prime organic chemistry right here. Now we're getting into the nitty-gritty organic chemistry, the bane of everyone's existence when you go to university. Who's going to do chemical something or other when you go to university? Sophie, yeah, you are, eh? Perfect, good, awesome. You're going to take a class called organic chemistry. Teacher's probably going to be, I probably shouldn't say this on record. Fine. That's different. But this is how organic chemistry happens. We get a lot of carbon to carbon to carbon to carbon bonds. Like that's how we get, like, for example, methane, ethane, pentane. I don't know if you ever heard of that. Propane, butane. There's a bunch of 4 carbons linked together with a bunch of hydrogens around them. That's butane. Okay? We get that from oil and gas, yes? Methane, natural gas would have a bunch of carbons with hydrogens. I don't know the exact formula for that one or whatever, but this is organic chemistry, right? So I'm going to obviously start here. Now, hydrogens are, I think, was this the example I had, or was it? Yeah. Now, hydrogens are easy to slap on anytime because they only form one bond, yes? So I'll slap them on when it becomes appropriate, basically, but I know that I have to connect these 2 carbons together. Is there going to be a central atom? The answer is no. There's 2, okay? Sometimes you're going to have to kind of split up molecules into 2 different parts. And then I think to myself, okay, where would it make sense to put a hydrogen? Well, probably here, because I don't want to put them, and I don't want to put them on the same atom, because if I do that, what's going to happen, look, don't do this, but if I did this, look what's left. Is that going to match up nicely? No, I mean, that's kind of, the other thing we have to keep in mind here is that molecules are for the most part, they like to be kind of symmetrical, for the most part. That's how we get the sharing, that's how it kind of balances itself out, yes? So I'm going to put the H there and connect those. And then, of course, whenever you see dots by themselves, chances are we got to put them together, right? So I'd probably take these 2 out here, put them there, and I'd say, oh, let's take those 2 out and share those as well. We get a triple covalent bond, yeah? Triple covalent bond. Each one's got 8, each carbon's got 8 there, and the hydrogen's got 2, right? Perfect. Good? Okay. So remember, if you got, like, if it's C2 or C3 or C4 or C5 or whatever, probably put the carbons together, because then that opens up a whole other realm of possibilities on the outside to connect stuff to, okay? But that's kind of what we want to do. The last one, now this is the last one, I promise, that I'll show you is sometimes they don't work out particularly well. In other words, this one here, we're going to do. And when you look at that, you're probably thinking to yourself, I don't know, what are you thinking to yourself when you look at that? Uh-oh, exactly. This could be troublesome, yes? Because it's got an uh-oh in there. Huh. And OOs lead to mistakes. Ha! Ooh, tough crowd today. So, what else do you see? What else do you think? Why wouldn't they just? I don't know. Why wouldn't you just? Why'd they put HCOOH? Why? Is anyone thinking like, why wouldn't you just write it like simpler? Yes? Yeah, H2CO2, right? Which is actually a carbonous acid. Yes? And you're thinking, well, why wouldn't they just do that if you put that into water? And the answer is, of course, why do you think? Why would you think they would label it out like this? Yep. Nope, it's not, because it doesn't have a charge. Why do you think they labeled it out like this for you? No, to make it easier for you to draw, right? They're saying, hey, they're basically saying, hey, by the way, you might want to consider putting the H on the C there, connect it to the O, connect it to the O, connect it to the H. That's kind of what they're saying. There's a problem with that though, but that's kind of what they're kind of hinting at here. Sometimes compounds, like, like acetic acid, CH3COOH, the reason they do that is because that's the way it's formed, C combined to 3 H's combined to, what's next? CH3, C to combine to an O, to an O, to an H kind of thing. That's kind of how it goes. This right here, I don't know if you remember this. If you were in my Science 10 class, I probably told you this at some point, that's probably pretty typical of an acid, that COOH thing there. That's a carboxylic acid, which is organic chemistry again. Chem 30, there you go, right? Look at you guys learning Chem 30. But for us, we got to draw this. So I would probably start with, well, probably a C. That's always a great place to start, and that's going to be my central atom. Now, you're thinking, well, I'm going to throw an H on there. In fact, I'm going to put it right there because it's kind of HC. Yeah, that makes sense. And the next thing I'm going to probably do is an O. Now, I'm going to caution you here. I would suggest maybe stop drawing I would stop drawing at this point. Okay? So I'd probably put an O on. That takes care of this guy here. Yes? Now, here's the beauty. Okay? We can add up electrons too if you want to, but pencils have erasers, and they make pens with erasers now too. So if you draw it wrong, you just erase it and try it somehow different, right? That's always an option too. So it says HCO and then O. So I'm thinking, well, I probably should attach the O to the O and then to the H. But I'm going to show you what happens if you try this. Now watch. Now, like I said, this is going to be not probably, and notice I kind of just turned it. I turned the O so they kind of match up with the electrons, yes? Okay. And then I'll put an H on there because that's kind of the HCOO. I'll put the H right here. Now, first of all, did C really become the central atom there? Not really anymore, is it? Like, it's kind of like, it doesn't look very central to me anymore, does it? But, here's what happens, right? So we're going to connect these two and connect these two and connect these two. And you're like, hey, that looks pretty. Oh, wait. Does that look good? Anytime you got electrons, and look, here's the issue. If the electron was over here, it wouldn't be an issue because I just make a double bond, yes? But when the electrons are on the same atom, well, how do you fix it? And the answer is, well, that is how you fix it, okay? So that's where you kind of have to be like, oh, wait, that's not going to work out. But it will work out. You saw we had 2 electrons. They can pair up. We just got to make sure they're in the right spots. Yeah. I'll tell you what, you wait and see. So I'm going to put my O there still because it's HCO. But instead of putting the O on that O, I'm going to go back and try and make carbon kind of the main feature again here. So I'm going to put my other O here just to kind of, central atom here, 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 like so. okay? Now, that takes us up to this part here, right? I still need one more H, but I'm not going to worry about it right now. I'll leave that off for a second. So again, I look at this and I say, okay, I need to make a molecule, so I need to connect these two and these two. And now, look, can I make a double bond here somewhere? Probably, yeah. And some of you are thinking, well, I want to make a double bond from here to here. Some of you didn't even realize that you could do that, or weren't looking at those two. Sure you can. Go ahead, do it. The H will go here, yes? Or some of you are looking at these two and saying, hey, let's make the double bond there, which is probably a little more common. So I'm going to take those two out, and I'm going to put a double bond there, yes? And don't forget, I still have the H to put on. Well, look, there's one electron here. There's an H there. Boom. Okay? Now, you know, again, you just double check when you're done. Does each carbon, every element have 8? I mean, that's the ultimate goal, right? Does hydrogen have 2? Yeah. Does each carbon, the carbon has 8, the oxygen has 8, the oxygen has, look right here. In fact, I can do this. There's 2. There's 8. That's a big stretch there, but that's the 8 there. Okay. There's 8. There's 8 right there, and there's 2, right? And that's how they overlap each other. And you might say, what if I put the H down there? It's actually the exact same molecule. Just turn it. Doesn't matter. You can turn them, you can flip them, et cetera, et cetera. Doesn't matter. And the beauty thing is, you can check your own work. And as long as you have 8 and 2 in the appropriate spots, you're going to get it right. Because I can't argue against you. Yeah. So that's up to you, right? Now, if you wanted to, you could add up electrons as well. But I'm going to tell you, by the way, this probably is not the best diagram because look, this is the carbon, and I didn't really spread these out. It doesn't matter for now, but this is kind of what we would, that's kind of what we would draw for that one to kind of spread stuff out around the carbon, okay? And yes, carbon, you know, yes, there's an H attached to the O there at the end, but carbon's still kind of the central atom, kind of per se, all right? It's not perfect, and yes, technically O doesn't really look like that, et cetera, but that's kind of the idea there, okay? Is that okay? Questions, anyone? Like I said, you know, a lot of these are pretty simple, pretty straightforward, and they're going to match up pretty nicely, okay? So I wouldn't expect anything like that right now, but you know, that's kind of how it works. 8 electrons or 2 for the hydrogen. Okay. Here's your homework. I just need, before you start going crazy here, I need to talk to you about 2 questions, real quick. There's only 8, but listen, just look up here for a second, please. This one says arsenic. Now, how many valence electrons does arsenic have? I guess is the question. How many valence electrons does arsenic have? Just pay attention for now. You can copy after. You got lots of time. You got half an hour-ish. How many valence electrons does arsenic have? Nope. Close. On the right track. Can't go above 8. 5. Yes. How do you know it's got 5? Because it's in the same column as nitrogen, phosphorus, arsenic. They all have to look the same. They're all 3 short. Yes. So because they're all 3 short, they have to look, you're going to learn there's only 6 shapes. Why is there only 6 shapes? Because there's really only 6 ways we can combine these elements together with a central atom. Like nitrogen, if it's in the middle, phosphorus is in the middle, arsenic's in the middle. They all give you the same kind of shape in the middle. Like that's the whole point. So there's only certain shapes that go with these compounds. So arsenic would be the same as phosphorus and nitrogen, just like oxygen, oxygen, sulfur, selenium, tellurium would all look the same. And so does fluorine, chlorine, bromine, iodine, acetine. They all have 7. And so do all the noble gases except for neon, or heon, except for heon, which is a new, no, except for helium has 2. Everything else has 8, right? So keep that in mind. And the second one I need to talk to you about is this. This is chlorine, okay, Cl, N, and O, yes? Those are the ones I want you to combine together there, okay? Good. So let's put it back here, and you guys can work on those for a little while here, okay?